Welcome back, everyone. So far, we have only mentioned the term conditional probability without properly explaining what it is. Conditional probability is the likelihood of an event occurring, assuming a different one has already happened. In this lecture, we are going to show you how to compute and interpret such probability. Let's go back to the coin flip example from the last lecture. A represents getting heads, and B represents getting heads on the previous flip. The probability of getting heads now, after getting heads last time, is still 0.5. Therefore, P of A equals P of A given B. This is equivalent to saying the two events are independent. Earlier in the course, we also mentioned that if any two events are independent, the probability of their intersection is the product of the individual probabilities. Now, let us examine the Queen of Spades example from last lecture, where A represented drawing the exact card, B represented drawing the correct suit, and C represented getting a queen. Normally, the probability of drawing the Queen of Spades is equal to 1 over 52. However, it increases if we know it's a spade. Since P of A given B is 1 over 13, and P of A is 1 over 52, we can say the two events are dependent. Similarly, because the probability of drawing our desired card alters if we know it is a queen, we can say A and C are also dependent. Let's formalize these observations with a formula. By definition, the conditional probability of an event A given an event B equals the probability of the intersection of A and B over the probability of event B occurring. This holds true if the probability of event B is greater than 0 only. And logically so. If P of B is equal to 0, then event B would never occur. Thus, A given B would not be interpretable. Now, let's look at the conditional probability formula more closely. If we compare it to the favorable over all formula we have been using so far in this course, we can see many similarities. To satisfy the conditional probability, we need both events B and A to occur simultaneously. This suggests that the intersection of A and B would consist of all favorable outcomes for this probability. Secondly, the conditional probability requires that event B occurs, so the sample space would simply be all outcomes where event B is satisfied. Everything fits into place now, doesn't it? Great. Once we know the intuition behind the formula, we can focus on the importance of conditional probability. Firstly, try to remember that the order in which we write the elements for the conditional probability is crucial. P of A given B is definitely not the same as P of B given A, even if the numeric values are equal. For instance, let's explore the characteristics of Hamilton College's class of 2018. 5% of the students who got a degree in economics graduated with honors. At the same time, 5% of all students who graduated with honors completed a concentration in economics. These two statements might have the same conditional probability, but they hold completely different meanings. In particular, the first one suggests that only 4 of the 80 economics majors graduated with distinction. The second one suggests that 4 out of the 80 students who graduated with high grades completed a degree in economics. Before we move on to more complicated interactions between probabilities, we are going to explore some real-life examples. See you in the next video, and thanks for watching.